Thank you very much, Massimo, for this generous and kind introduction. It's my pleasure to give this colloquium today. Since the size is not too big, it would be perfectly convenient to have the talk. Please feel free to mute yourself and ask it. So I assume that now my screen is shared. Yes. Okay. Very good. So so I'm going to talk about something that's very dear to my heart, which is connections between the string landscape and also the idea of what does not belong to the landscape, which is the swampland. So quantum field theories without gravity included are well understood, and they beautifully describe the interaction of all elementary particles we know. We have the Feynman diagrams capturing all these processes, and we get nice answers, and we know what it means to have a good, consistent QFT, as long as we don't have graviton or gravity in this mix. To include gravity, in this case, of course, what I mean is Einstein's theory, what we need to do is to, in the context of quantum theory, we have to couple the quantum field theory to gravity, which means that instead of having a fixed background, we take a fluctuating background where the particles are scattering off each other, but at the same time, there will be fluctuation of the background, which what this means practically is that you take the Lagrangian and you view a metric appearing in whatever Lagrangian you had for the matter, the gauge fields and fermions, etc., and add to it the Einstein term and integrate over the metric as well. In other words, in the path integral, you have a dynamical gravity. Well, this approach, unfortunately or fortunately, whatever the case may be, does not work. And the infinities that appear in Feynman diagrams are incurable. And so a conventional approach to quantizing gravity does not work. And this was discovered already a long time ago, around 60 years ago or so, by Feynman himself. And the most natural conclusion a theorist may have drawn from this is that gravity cannot be coupled to quantum fields. Gravity is inconsistent with quantum theory. But of course, that's not acceptable simply because we know we live in a universe which does have both gravity and quantum mechanics dynamically. So we have a dynamical graviton and quantum mechanics. So they should exist consistently in some form. It's our universe, after all. So this is not an acceptable answer. So of course, Feynman did not say quantum field theory cannot work to gravity, but he couldn't make it work, let's say. String theory offers a solution by the idea that if you replace the point particles by these extended object strings, somehow the inconsistencies of this quantum theory of gravity disappears. And in the context of Feynman diagram, it simply means replacing the Feynman diagram. So we have these usual nice Feynman diagrams, and you replace it by what we call the string diagrams, where each word line is replaced by a word sheet, which is this tubes, and these strings come and split. The nice thing about it is that it kind of unifies all these particles and their interactions into simply the geometry of these nice surfaces. So it's very appealing and aesthetically pleasing to have a simpler description, at least theoretically, of what these diagrams are. So this gets rid of the inconsistencies of mixing the gravity with quantum theory. And part of the idea is that these diagrams, which give you singularities or infinities, where you make these points come close together, like in loops of zero size, disappear here because of the finite size of the string. Roughly speaking, string size provides a natural automatic cutoff to avoid these infinities. But then it raises the question whether we can get an arbitrary consistent quantum field theory in 4 dimensions coupled to gravity from string theory. String theory comes with 6 extra dimensions. So we have 3 + 1 space-time dimensions, but we have also 6 extra that nobody ordered, but they are there. We cannot avoid them. And these should be viewed as, if we want to avoid the contradiction with the experiments, we should view them as compact, tiny spaces which have not been detected so far because they're so tiny. Many solutions exist in string theory to what these extra dimensions could look like. These are some cartoons of what these spaces look like. They're very complicated, and of course, I cannot do justice to drawing a 6-dimensional space here, and neither can this cartoon show it either. But here it's illustrated that the macroscopic dimensions are these yellow directions, these yellow grids. It's compact space, and so tiny you can kind of not measure it. It could have been different compact spaces at different points, but at low energy, you just pick one of them, and it's just a constant in space-time. Now, depending on what space you have picked, there will be different excitation modes of strings, depending on how they wrap over different cycles. At any given point, you can wrap strings around these cycles or other objects that appear in string theory, membranes, D-branes, and so on. And they give you different particles and with different properties depending on which shape they take. And overall, depending on which compact space you pick, you have a totally different 4-dimensional physics. So for example, if you want gauge group SU4 with 2 generations of matter, etc., you may choose a particular shape and size, etc., of this internal space. Or if you want a different group, maybe you choose a different one with different representations for particles. The question is raised is whether or not you can get arbitrary consistent quantum field theories by choosing something as this tiny compact space. It seems that we cannot get arbitrary quantum field theories by using an internal space. Indeed, from string theory, we seem to only obtain a finite number of quantum field theories from string theory. So there's a finiteness, surprising finiteness condition, unlike the quantum field theories, for which there are infinitely many of them. For example, suppose you're interested in the case of, in 4 dimensions, when you have maximal amount of matter supersymmetry, and that's n equals to 4 supersymmetry Yang-Mills. This is one of the most beautiful quantum field theories in 4 dimensions. In fact, due to the high amount of supersymmetry, this theory is finite and has very nice non-renormalization theorems associated with this. So it's a very, very, very elegant theory, and it makes sense for any gauge group in 4 dimensions, except we don't seem to get any of them whose rank is bigger than 23 from string theory. In particular, if you consider the gauge group SUM with m bigger than 23, it does not arise in string theory as being coupled to 4-dimensional gravity. So if you said, okay, I want a universe which has n equals to 4 supersymmetric Yang-Mills with gauge group SU25 coupled to 4D gravity, sorry, you're out of luck. String theory says, I cannot give it to you.
Sorry, Cumrun, why 20? So what at 23? Because what at rank 23? Are they allowed non-perturbatively or not?
They are not allowed. So they are not, no rank higher than 23 is allowed. And just to be clear, I'm talking about theories coupled to gravity in 4D. So of course you can obtain 4-dimensional n equals to 4 Yang-Mills on D-branes, for example, in 10 dimensions. You can get any of them, for any n you can get it. You can get, for example, SUN for any n if you put n D-branes on top of each other. But if you want to have a compact space, intermediate space, that requires, turns out, to have a finite number of possibilities, and the rank is bounded. So there's no way we can get any rank bigger than 23 in string theory. So this is already surprise. So it's not that the quantum field theory is bad. This is a finite theory. It cannot be any better. But nevertheless, you cannot couple it to quantum gravity in 4D. So that's a surprise. So it's not because of the badness that this happens. Quantum gravity brings new issues into the fore that is not obvious from the viewpoint of quantum field theory. You cannot just add graviton and just say, well, we will couple them and it's going to work. It just doesn't. In fact, the quantum field theories that you get from string theory form a measure 0 of consistent quantum field theories. Just like in this example, the consistent ones are from rank 1 up to 23, but the allowed ones are from 1 to infinite. So clearly the ratio of the finite number to infinite number is 0. So the measure of allowed consistent theories is 0. So it appears that Feynman was almost right. a generic consistent quantum field theory cannot be consistently coupled to gravity. So that is the main lesson of what we have learned in the context of string theory. So that Feynman was essentially right. It's only very rare exceptions to the rule. There are only very rare consistent quantum field theories that you can couple to gravity. This raises two questions. Does the fact most quantum field theories do not arise in string theory a deficiency of string theory, or a general conclusion about consistency requirements for coupling to quantum gravity? You see, because it could be that they're consistent. It's too bad that string theory can't get it. Evidence is emerging that this is not a deficiency of string theory, but subtle reasons for consistency of quantum gravity prevents them from happening. And it's precisely these subtle reasons that I want to describe here today. Connections with basic facts of quantum gravity mandate such a conclusion, including issues such as unitarity and quantum consistency of black holes. So some issues which are beyond string theory, like kind of calculations that already Hawking did in 70s, which was demanded by semi-classical treatment of black holes, taught us basic facts about black holes, which turn out to have ramifications which are related to these finiteness issues I'm mentioning here. So then naturally the question is, okay, if there are some special criteria that you need to have for a good quantum field theory to be part of a good gravity or string landscape, from the bad ones, which are the quantum field theories which cannot be coupled to quantum gravity, which we call the Swampland, which ones are? What are these criteria? This is what is called the Swampland program, to try to delineate these conditions, which tell you what are the good theories and what are the conditions that will tell you that cannot be possible in a good theory coupled to gravity. So in a sense, we have this vast space of quantum field theory which is consistent, and only under very small set of possibilities coming from these compactification, you can get a consistent theory. Like in this example, like this image here, if you think about this green space as the space of all consistent quantum field theories, essentially all of them belong to the Swampland, except for finite number of them, which we call the consistent quantum gravity landscape. And hopefully, of course, one of them is our universe standard model. But this is part of a very finite set. Now, this is very crucial point of view, a change of point of view, because usually when we look at our standard model, from the vantage point of all possible consistent quantum field theories, it might appear to have very bizarre features. Features like hierarchy, features like fine tunings. And people for many decades now in particle physics have been trying to find good reasons to explain these fine tunings with unfortunately not much success. So some of these big vexing issues of fine-tuning issues of quantum field theories is not resolved. And it appears our standard model has been very isolated in terms of naturalness issues. However, if the set of possibilities corners you to a very narrow subspace, and that narrow subspace already has some bizarre features of the standard model, therefore it won't be fine-tuning within that subspace to be ending up with a standard model. So this puts a completely different perspective about issues such as fine-tuning in the context of regular particle physics. So understanding these conditions is crucial, and in some sense replaces the program of trying to find naturalness criteria to try to make our standard model more natural.
Can I interrupt with a question real quick?
Please.
Yeah, so at the beginning, you talked about, with Feynman, you talked about the problem was the, infinities that were incurable, but that was before string theory. And then you talked about string theory and coupling different types of quantum field theories there, and which ones are sort of allowed or consistent and which ones aren't. But I missed, what is it that goes wrong if you try to couple some, your SU, 25 to, what is it that's going wrong? Is it about kind of a...
I will describe some of these features. That's the point of my talk here. Yeah, exactly. So what goes wrong will be some of these conjectures that I'm going to mention don't work, and why these conjectures are natural, or why we think it's necessary. I'll try to explain. So in fact, we have now found the reason from these conjectures why SU higher than 20 three are not allowed, and they are really inconsistent. So that's how we come to that conclusion is very surprising from a particle physics or a low energy quantum field theory perspective. I can give you, well, I will give you more examples as we go along. So let's come back to it. But now, so what are these criteria? So at least I have to begin to enumerate some of them. First of all, I have to point out we don't know all these conditions. In fact, we expect them to be infinite number of them, perhaps. We don't exactly know what is a good organizing principle for finding these requirements for which distinguish the landscape from the swampland. But here are some that we have discovered that I'm going to talk about today. There are more than this that has been discovered, but I'm only going to talk about these because of the time limits. And I will start with some of the ones which are kind of more easily arguable. So some of these we have more arguments, some of them we have less. So there's a kind of we don't have enough equal amount of evidence for all of these criteria. Some of them are more, we have more evidence, some of them we have less evidence, and so on. I will try to explain what are the motivations for some of these statements and how they relate to each other. Yes, Glennis.
Hey, Cumrun. So just to be sure I'm clear on what you mean by the landscape, do you mean with the 3+1 dimensional space-time large, or any consistent string theory?
We consider any consistent string theory. So we talk about different dimensions as well. So for my talk, I will focus mainly in 4D, but the statement is really for any D.
But I mean, these requirements aren't, I'm wondering, are there extra requirements you have to impose to get into 4D?
Not really. I mean, the conditions that I'm going to tell you about here today hold for any dimensions.
Oh, thank you. That was the question.
Yes. Thank you. I should have said that. So these are consistency conditions we believe for quantum gravity in any dimensions. So first of all, there are no global symmetries in a consistent theory of quantum gravity. Secondly, so first of all, I will not explain the motivation yet. I will first enumerate them, and then I'll come to one by one. I'll go over them by why we think these are correct. There are no global symmetries. So if you end up with having some symmetries, then they better be gauged. Secondly, is we believe that there are no distinct quantum gravities. Any two different quantum gravities are actually tunnelable from one to the other with finite action processes. So the quantum gravity in some sense is unique. It's one theory. This is related to cobordism conjecture. Third, all gate charges appear in the spectrum. So if you have a gate symmetry, every charge that you can allow, that gate symmetry allows, must be, all the representations must appear in the spectrum. You cannot pick and choose. It should be all there. This is the completeness hypothesis. The range for the fields, effective range for the fields is finite. You cannot have a consistent effective field theory with infinite range for the scalar fields. This is related to the duality conjecture or distance conjecture. The theory admits light higher dimensional objects. You cannot have a theory only of particles. You have to have higher dimensional objects. This light, I don't mean necessarily light, just some higher dimensional objects, like could be membrane, it could be string, something. You cannot just do particles. String theory is an example, but it could be other things. It cannot be particle theory. Gravity is always the weakest force. Just like our universe, gravity is the weakest force. This is called the weak gravity conjecture. And there are restrictions on critical points when you have positive potential. And these will have some cosmological implications, and these are related to what's called the de Sitter conjectures. So these are the topics I'm going to cover. So let me start, before going over them, by reviewing some basic facts about black holes. If you fix a charge and mass for a black hole, there is a black hole as long as the mass is bigger than the charge. I'm measuring the mass in Planck units. And here I'm doing it in let's say we're dealing with the regular 3+1D physics. And there's an extreme case where the mass is equal to charge. These are called the extremal black holes. Black holes have a thermodynamical property, as was discovered by Bekenstein and Hawking, which means that they carry entropy. That means there is an entropy that black hole, even though it might look like it's unique, but actually there's a huge number of states, associated with it, which is given by the area of the horizon of the black hole divided by 4. Now, you see already, just before I go any further, I want to point out some obvious fact. This is already known from 1970s. This fact already is mind-boggling. So let me explain why this should be mind-boggling. This already tells you that if you want to have a 4-dimensional pure modes, that theory is inconsistent with gravity. Pure Einstein theory with no massive excitations cannot be consistent. Why is that? Well, because you can consider black holes, and according to Hawking-Bekenstein formula, there is entropy for them. That means there must be such states in your theory. So this is already remarkable that just these simple facts, so IR physics, which in this case is the black hole physics, is predicting UV physics. There must be states which are massive. Surprising, but this is already known. This has nothing to do with string theory. This goes all the way back to 1970s. This we already knew for many, many years ago. Okay, so let me start. There are no global symmetries. That was the first criteria I mentioned. So how do we see that? Well, suppose you have a global charge, Q, and suppose you throw this global charge into a black hole. When it falls into the black hole, since it was a global charge, there is no electrical field or anything from outside we can measure to determine what's inside. In other words, this looks like any good old black hole with a given mass, and there's no sign of signature of the charge in it. And so according to Hawking, this black hole radiates away. And since there's no charge, there's no electrical field outside associated with this charge, it radiates equally positive and negative charges of this type. So therefore, the evaporation process is charge neutral. And therefore, we end up with no charge at the end. And therefore, it means that that charge that we threw in disappeared. Therefore, that global charge is violated. The process of black hole absorption and emission basically violates this, this global symmetry. Again, this was the first thing I just told you. This, again, predates string theory. It's kind of arguments that people were using many, many years ago. It's not particular to us. But it's of course reassuring that in any time we see in string theory, all the symmetries we see are gauged. That's reassuring because that would have been a bit worrisome if it was inconsistent with this. In fact, not only continuous symmetries are gauged, but also discrete symmetries are also gauged. So all symmetries in string theory are gauged. Second criteria I mentioned, uniqueness of quantum gravity. This is a generalization of no global symmetries. Any consistent quantum gravity can be deformed to any other through a finite action physical process. So in the context of string theory landscape, this means that if you take the internal space of strings, compactify it, and if you take 2 different compactification, let me call one of them M and the other one N, there is a finite process which connects the 2. And this, when this happens, we say that M and N belong to the same cobordism class. That means that any two spaces belong to the same cobordism class, which means cobordism class is trivial because you could have also no boundary at all. And so therefore, this is the cobordism conjecture. Now, why is this a part of the global symmetry? No global symmetry. Well, this is in spirit the same as the no global symmetry condition, because if there were selection sectors that M cannot be connected to N, then you could associate charges to M's and N's. These are higher form charges, higher form symmetries that distinguish them, and that could not be possible. And therefore, we immediately deduce that cobordism classes better be trivial. Criteria 3 is that all charges that for a gauge, if you have a gauge theory in your theory, a gauge field in your theory, all the charges that can appear in a spectrum do appear. So suppose you have, for example, a U1 gauge symmetry. All integral charges Q are in principle allowed to be in your theory. Do they exist as states in your theory? Without gravity a priori, there's no reason. For example, we can easily imagine having a pure Maxwell theory with no charge states at all. Even if you couple it to gravity, you might have thought that what's the problem? You just have a Maxwell theory with no charge. What's the problem? The problem is, again, the black holes. So we know that at least if you have a big enough mass and charge, you trust the low energy effective description of a black hole. And according to Hawking, we know that the number of states is exponential in the area. So it's a huge number of states in your theory of a large mass and large charge. Well, you can take a large charge Q plus 1 and another large charge minus Q and throw them at each other. You get to collide the two black holes. You know, the charge 1 in your theory. So therefore, every charge appears in your theory. So black holes already predict. So if you wanted to just do Maxwell theory with no charges, you're out of luck. Quantum gravity is inconsistent. Criteria 4 is that there's a finite range for fields. Now, this actually is one of the deepest ideas that has emerged from string theory, and it is one of the ones which we have not as adequate an explanation as we wish, like black holes. And this is related to the discovery of duality symmetries in string theory, and it's related to what is called the distance conjecture. So these are properties that we know is true in every string theory we know of, but we don't have a simple explanation why. So let me explain what it is. Consider a field phi. Without gravity, we usually have no restriction on its range. Phi could go range from minus infinity to plus infinity. However, with gravity, it seems that the range for this field changes, and we give as long if you want to find an effective theory description, if you have an effective theory, it turns out that the range of phi is order 1 in Planck units. So if you want to increase the range of phi more than 1, then you're in trouble. Namely, your effective field theory should break down. It doesn't mean that you cannot get to larger values of phi. You can get there as long as you give up your effective field theory. Your effective field theory needs more and more degrees of freedom. But it's worse than that. Is that you can never complete that effective description, because as you go more and more into larger and larger distances, you get more and more and more degrees of freedom until you need infinitely many degrees of freedom, and your description, effective description, breaks down. So therefore, there is no consistent description which includes a infinite range for phi. So the one nice description of this is in the context of, you can describe it in terms of higher dimensional spaces. So let me talk about it that way. So if you have, suppose you have a scalar field space phi, it doesn't have to be just one dimension. So you can have a number of such scalar fields. And in the action, you will have some metric in this field space. This naturally gives you a space, a metric space of the scalar web. So you can think about this as a space of expectation value of the scalar field, which comes with the natural metric on it because you can read it off from the kinetic term in your action. Now, it turns out if you move of order 1 in Planck units in this theory, you will, in other words, in the phi, range of phi, you're fine, and you can give a description, effective description of this theory. But if you move too far away, you get to the corners in which no matter what you do, you get light states coming from massive modes. So you get a tower of these light states emerging. And their mass go exponentially down with the scalar field web. So as you go in the phi direction, you get a times e to the minus alpha phi as this mass scale for this tower of states. Now, why does this appear, and what does it have to do with the duality conjecture? Is that these light states are precisely the ingredients, the basic fundamental degrees of freedom of the dual description. So the fact that you have these different corners simply refers to the fact that each time you try to go to infinity, you get new degrees of freedom emerging and giving you a totally new description of physics. So the emergence of this tower at infinite distances is kind of the bread and butter of string theory discovery in the past 20 years, or 30 years, 25 years or so, the discovery of duality symmetries. A potential application of the distance conjecture is the following. So in the universe we live in, we know that the cosmological constant is not zero, it's positive. And you can view it in the context of string theory, it must be the expectation value of some field. And it turns out the natural metric on that space will go exponential with the field. So if we say lambda cosmological constant today is 10 to the minus 120 in the Planck units, this means that the Vafa phi is of order of 300. And this naturally is very small in some sense. And MV phi is much, much bigger than order 1 in Planck units. And therefore, you would naturally expect maybe some kind of a tower to appear. So the question would be, what is this tower I'm talking about in the context of a current universe? Well, this will suggest you would expect a tower of particles with masses which scale like a phi, but e to the minus phi is lambda, so that means you expect a tower of state which scales with power of lambda. So this is an interesting connection between particle physics, potentially, at least a tower of particle physics, with a natural tower dictated by some power of lambda. Amusingly, the neutrino mass is related to lambda to 1/4, which is quite unexplained in current theory of particles. It's kind of an observation that the mass of the neutrino and the dark energy are related in this way, but it didn't have to be. But this suggests that maybe there are these kind of relations that could explain these facts. The next criteria is the fact that a consistent theory of quantum gravity cannot be based on particle physics alone. It must be related, there must be extended objects in this theory. There must be extended objects like in M theory, where you have membranes or strings in string theory. And this also follows, at least heuristically, from the previous criteria in the following way. Namely, you can consider compactifying the theory. Suppose you start with the theory in higher dimension, you compactify it on a circle. In the one lower dimensional theory, you get an extra scalar, whose vev controls the radius of the circle in this way, and the action goes like 1/2 grad phi squared. So now the distance conjecture tells you that if Vafa phi is large, you have to get a light tower of states. So if you make phi large, you do indeed get a tower of states. And these are the light momentum modes of graviton, what are called the KK modes. So for r much, much bigger than 1, which is phi much, much bigger than 0, you get a light tower of momentum modes going around the circle with energy of the order 1/r, which means goes like e to the minus phi. So indeed, that's an example of the tower that I was talking about. This is the tower of what's called the KK modes. However, we can go the other direction. Namely, we can go to phi much, much less than 0. That's also infinite distance away if you go to minus infinity. In this case, r goes to 0. The duality conjecture predicts something should become light. If the distance goes to 0 size, a particle theory does not get any new states. In fact, if you start with any particle theory, if you put it on a circle of 0 size, it is what we call dimensional reduction of the field theory from one higher dimension to one lower dimension, precisely because the KK modes become infinitely massive in this case, and you don't get any new states, and therefore that's what you lose. You just lose all those states and you get the dimensional reduction, and there is no tower. So that means the particle physics is inconsistent with distance conjecture. And the way this is resolved in the context of theory is that it has to have some extended object which feels the global topology of the space. So if you put it on a circle, it should be that it's wrapping around the circle. So when the circle becomes smaller and smaller, the tension of the leftover object, if one leg of it is wrapped around the circle, becomes smaller and smaller because the tension of the leftover object or its mass goes down proportional to the length of the circle. And so therefore, that's how we get the tower of light states in the context of string theory, where the natural mechanism is that membranes or strings are wrapped around this extra circle. So this already suggests that the consistent theory of quantum gravity must include extended objects. Now, the next criteria is the fact that is one of the most, I would say, interesting perhaps of these criteria. Is the property what's called the gravity, weak gravity conjecture, which is called the gravity as the weakest force. In string compactification, it has been observed that whenever we have charged particles, the electric force between the elementary charged states are always stronger than their gravitational attraction. So if you have two particles, in string theory, we find that the gravitational attraction between them, which goes like m squared over r squared in 4D, is much smaller than electrical attraction, a repulsion between them, which is e squared over r squared. And this simply means is that their mass in Planck units is less than the electric charge. This is observed in string compactification, and it's also true, of course, in our universe, where, for example, the mass of the electron is 10 to the minus 23, and the electric charge is 10 to the minus 1. So as you can see, this is well satisfied in our universe, and so that's what it is. But the interesting thing is that this is not particular to our universe. The prediction that this is true in any universe, any would be consistent compactification or any consistent quantum gravity, we expect this to be the case. Now, criteria, and it turns out to be again black holes. Surprise, surprise. Always black holes come into the middle. Why do the black holes have anything to do with this? Well, let's start with an extremal black hole. Extremal black holes are when the case the mass is equal to the charge of the black hole. Now, if we assume the black hole has to decay, which is the natural assumption based on what Hawking has shown us, it's natural to expect that you emit charged particles, and with some mass and charge. If the mass and charge are sufficiently small, then you can presumably do this, and the big charge of the black hole goes to Q minus Q, and the big mass goes to M minus M. And what you find is that if you want to have the mass bigger than the Q, which is what we want for the black hole to exist, so if the leftover black hole is not to violate the no singularity of the black hole, you have to have M minus M bigger than Q minus Q, because it cannot be super extremal. And if that's the case, because Q was equal to M, it already implies that the mass of these tiny elementary particles goes the opposite way. That mass should be less than or equal to Q. So this we learned that we are expecting particles to have masses less than or equal to the charge. And it turns out there's a limiting case where mass is actually exactly equal to the charge. And the only examples that this occurs that we know of are in the supersymmetric cases. And in those cases, the black hole itself can be stable. In other words, the black holes, the supersymmetric BPS black holes are the only ones which we don't expect necessarily to decay. So the weak gravity conjecture is related to the fact that if you have a huge entropy of these states, if they are not stabilized by any black hole, if they're not stabilized by any supersymmetric reason, they better disappear. They are unstable. Otherwise, you have a huge number of remnants with no supersymmetric reason or anything. And this would be strange from the viewpoint of quantum gravity. Now, there is further evidence for weak gravity conjecture. In particular, pure Maxwell theory coupled to Einstein gravity leads to naked singularities. Naked singularities are singularities in the general relativity which are not hidden behind the horizon. And if you take just a pure Maxwell theory and couple it to gravity, and if you consider regions of strong electrical fields, you find that this principle gets violated. This is what's called the cosmic censorship principle, that you should never get naked singularities. Well, this was the principle that Penrose had suggested a while back, and we don't have a proof of that, but it turns out that the weak gravity conjecture actually resolves this paradox with the cosmic censorship. And the way that goes is the following. You see, if you have an electromagnetic Maxwell theory, from what I told you, there should be a complete spectrum of particles. Therefore, all the charges must appear. So that's the first step. The second step is that the weak gravity conjecture implies that they cannot be too heavy charged states, because there should be mass, because we just said that there should be light states, elementary excitations whose mass is less than or equal to charge. Third, when electrical field becomes large, then when you got singularities here, because there are these charged states whose mass is less than their charge, they can be easily produced from the vacuum because they're light compared to their charge. And what happens is that when you produce them from the vacuum, they screen the electrical field, they get rid of the singularity of the electrical field and avoid the naked singularity. So this is an interesting way that the weak gravity conjecture with the completeness of spectrum leads to cosmic censorship in this situation, even though this is just a classical GR. So these quantum facts about black holes are kind of becoming consistency conditions for some of these principles that seem to be cherished by GR people like Penrose. Let me give you another application of the weak gravity conjecture to our universe. In the Sitter space, where we have positive cosmological constant or positive, what we could call dark energy, we could also consider black holes. So here I was talking about the black holes in the context of Minkowski space, but let's consider them when you have a curved space. The conditions that I was telling you about apply to small black holes. And if you take small black holes in de Sitter space, you get the condition I already talked about. Namely, you find that there must be states whose mass is less than charge. However, if you consider big black holes whose size is the same as the size of the horizon of the Sitter space, you find, by studying the corresponding charged black holes, what's called Neraian black holes, you find that their mass cannot be smaller, it's a lower bound, given by the dark energy to the 1/4 times the charge to the 1/2. So therefore, you find a lower and an upper bound for a mass of charged states if you have non-zero dark energy, as in our universe. So in our universe, if you take the cosmological constant value and the q to 1/2, you compute the left side in Planck units, you find this is 10 to the minus 31, q is 10 to the minus 1. So you find that there should be elementary charge excitations whose mass goes like between 10 to the minus 1 and 10 to the minus 31. Indeed, electron is in that range. So it's consistent with this statement. Of course, it is nothing to write home about in the sense that it is not a sharp prediction. It's not a very, it's a prediction for sure, but it is such a big range, it wouldn't be something that anybody would be too proud of. But at any rate, it's certainly interesting that we're coming up with criteria which bounds upper and lower a given existence of a given particle. Interestingly, this lower bound for the mass is what we know for the mass of the neutrino. The mass of the neutrino is about lambda to the 1/4. And this is already surprising. Of course, we cannot use this just to derive this for neutrinos, and the reason is that charge, so we cannot apply it to our universe as is. It would be interesting to try to use electroweak symmetries and so on to try to extend this argument to somehow apply it perhaps to neutrino as well. So the last topic I want to talk about is restrictions on critical points for potentials which are positive. Or, so this is one thing I want to talk about, or if you have a potential which is positive, how flat can the potential become? This is an important question for early cosmology in the context of inflation, or late cosmology in the context of dark energy for our universe. A natural scenario in the context of early universe cosmology in the context of inflation is to have a potential which is relatively flat for a range of field range, and it settles down to a minimum, and the minimum being of the order of the dark energy that we measure today. So this is a kind of a simple model, very simple model, where it explains both the early universe and the late universe in terms of the potential of connection with inflation as well as the dark energy that we observe today. Okay, now let's go back to the general question, what do we know from string theory about the situation where the V is positive? Unfortunately, one can show that if V is positive, supersymmetry, which is one of these cherished properties of many backgrounds in string theory, must be broken. It is not a problem. We can break supersymmetry in string theory, but it turns out whenever we break the supersymmetry, we generally lose analytic control, and we don't know exactly everything we need to know. Unlike the supersymmetric case, where we often can know exact understanding of the space of light degrees of freedom and phi's, analog of the moduli space of scalar fields. It is kind of our bad luck that this is for positive energy where we live in. You see, if it was negative energy, it turns out there are perfectly good situations where you have a supersymmetry with negative energy. So negative V is no problem with supersymmetry. You can find easily backgrounds which are supersymmetric. It's only because of this silly sign, if you may say, of the dark energy that we cannot do this. So in our universe, we are on the wrong side or on the difficult side of this problem. We have to break supersymmetry just because positive cosmological constant. So we lose analytic control. So what do we do? Well, one thing we can do, we still can go to weak coupling regime of string theory and study it there. So how do we go to weak coupling regime? Well, there's coupling constant in string theory. We can, for example, tune it to extremely small value. Coupling constant in string theory, like any other constant, is not really a constant, it's the expectation value of a field. So you can always go to an extreme limit on the field value to make the coupling weak. So in other words, you're ending up on a space like this, and you can go to extreme values of the coupling constant and break supersymmetry and see what you get. When you do that, you can have a reliable computation in this weak coupling regime, and you find that you get goes to zero. Sometimes it goes to zero from positive side, sometimes it goes to zero from negative side, but it always goes to zero. This is quite remarkable. You see, there's no a priori reason it had to, from the viewpoint of quantum gravity. You could have naively thought that there could be any kind of potential. Why doesn't the potential go to plus infinity at large distance? Why does it always have to go to zero? In fact, more than that, one sees that this potential goes to zero exponentially fast. So in other words, V goes like e to the minus some constant times phi, where this constant in Planck units is of order 1. Indeed, one can show using general string compactification analysis that the slope V prime over V, that is that value of that C in Planck units, is bigger than square root of 2/3. So there's a lower bound on how small the C is. So in other words, this really fast goes to zero for far enough in phi. But just related to Glennis's statement, the value square root of 2/3 depends on dimension. Here I'm quoting the answer for dimension 4. For other dimensions, there's a D dependence in this formula I'm not writing. Now, this is already quite interesting, because this means that we are predicting from string theory that there is no stable model of dark energy. That is, even if you have a quasi stable or metastable de Sitter space, there is a lower energy state in your theory that you can decay to, and therefore this cannot be absolutely stable. So we are predicting that therefore our universe, which has positive dark energy, is not stable. That's a very strong prediction, I would say, of string theory. Unfortunately, it's not a prediction we would be happy about, perhaps, but we are making a prediction regardless of what kind of details we have inside. We will have to decay. We are not going to be ending up forever in the universe. We are expanding forever. Okay, now, question is, do we know what's exactly going on inside when you go to regions, not to the infinity, but actually to the middle of the space? But before I get there, I want to point out that this slope condition I told you about, that V prime is bigger than constant times V, fits very nicely with this distance conjecture or duality conjecture, where you get a tower of light states. You see, if you get a tower of light states whose mass goes like e to the minus a constant times the phi, since the potential gets contribution from the tower, generically of the order m to the 4th in 4 dimensions, we expect, therefore, the potential to go like e to the minus 4 a phi, and so therefore, indeed, exponentially goes to 0. So this is very natural from the viewpoint of the tower conjectures. Okay, so what's going to go inside? Let's just ask that question. Well, this is the notoriously difficult question, and still being debated, unfortunately, by string theory community. We don't have a clear answer. There are some suggestions about what we could possibly get here, but we don't really have a full answer. So let me just say what are the possibilities. First possibility is that there is no restrictions inside, that anything goes. Even though we know that this is not the case for asymptotic values, it could be that inside there's no restriction. This is unnatural, given the very specific boundary conditions that we're getting for V. So there's something about an instability of the V that is kind of intrinsic in this theory, and it'd be surprising if there are no restrictions. But it is possible, and we don't have a good reason to rule it out. There are two other suggestions that have been proposed that would say that, no, there's something also unstable from the middle. One is to say that this condition V prime is bigger than a constant times V that we know is true for large field values is also true inside, as you go inside the space. Or if it's not true, if you find that, for example, the 0 for V prime is always the unstable type, not the minimum, but the maximum for V. Not only a maximum, but the maximum whose value, the second derivative, is sufficiently negative compared to V. So this is what's called the de Sitter Swampland conjecture. Another version of this conjecture is what's called the Trans-Planckian censorship conjecture, which suggests that perhaps what's happening is that if you have a potential, no matter what potential you have, since potentials lead to expansionary universe, you should never end up with a situation after a long time of expansion, you end up with a space so big that a sub-Planckian, things which are smaller than Planck distance, which quantum gravity forms take over, should not become bigger than the horizon at the end and freeze out. We don't have a proof why this should be the case. This is just a criteria people have explored. And it turns out that if you just take this simple principle, you'd obtain exactly the bound that has been obtained from string theory for the asymptotic values for V. You find asymptotically V prime over V should always be bigger than square root of 2/3. So this is not a proof of this conjecture, but at least it's circumstantial evidence that not only it fits with string theory, it actually gives the numerical values that has been observed from string compactifications. So there are candidate constructions in string community, which actually violates both the second and the third one. For example, scenarios called KKLT, which people are still debating to what extent it's reliable. The issue there is that people are debating whether or not it's under analytic control. So we really do not know which one of these are actually true. But these are the scenarios we have right now. So let me just try to explain what kind of predictions the second and the third criteria give you. So this is swampland conjectures, and inflation, even though it doesn't rule out inflation is not ruled out, but the typical scenarios seem at least highly fine-tuned. And for example, the duality conjecture leads to prediction that we cannot have a naturally large field inflation because you get a tower of light states that interferes with inflation. But there are ways to come around it, get around this. For example, multi-field inflation is one way, and there may be other ways. Another thing is the slope conjecture that explains that the slope is hard to get. At least if you take the de Sitter conjecture, the slope cannot be too small. It's order 1, but again, in the simplest models like plateau models, you're looking for slow roll kind of situation where it gives you the value of C be less than 0.02, which is possible inside, I guess, because it's not bounded from like square root of 2/3 inside the moduli, but it's a little too small perhaps. And if you take the Trans-Planckian censorship conjecture, you find the unnaturally small potential scale for inflation of the order of 10 to the 9 GeV, which makes inflation very unnatural. The initial conditions for inflation should be fine-tuned for this to really work, and it leads to very bizarre values for the epsilon and the slow roll parameter and the R parameter, which controls the tensor modes in inflation. So this I would say is TCC is kind of incompatible with inflation, at least with some fine-tuning issues or some bizarre values. So I would say that there's some tension with inflation. So you might ask, if it's not inflation, then what could be going on in early universe? You see, inflation is basically trying to solve what's going on if you extrapolate backwards our universe. And the problem is that you want to have a effective theory, a single effective theory, which is valid all the way down to 0 radius of the universe. However, this may not be possible. In fact, more than that, we expect such a thing to be impossible in string theory. Why is that? String theory tells you that when you go to extreme limits, when you take the expectation value of fields to infinity, you will have to get a tower of light states and a dual description. Early universe constitutes going to 0 radius for the universe and infinite temperature. These are infinite distance. For example, temperature is dual in Euclidean space, so inverse radius. So this is literally a situation where we know it's not possible to avoid massless states. You are going to get light states, and light states give you a dual description. So string theory basically tells you, if you want to get a simple effective theory, including our universe standard model, with finite number of degrees of freedom to describe the early universe, you're out of luck. You should be out of luck. In other words, what was one of the main motivations for theories like inflation was simplicity of adding just a few fields and making it work. Here we are learning, at least from string theory, that's not a good motivation. In fact, you look for the opposite motivation. You expect the theory to break down. You're looking for the breakdown of the standard model. And so therefore, there are more natural scenarios in string theory, for example, string gas cosmology, where when you shrink the universe, a dual space takes over, where the inversion of the length happens, where over and not the degree that we're made of. And the degrees of freedom of our theory, the standard model degrees of freedom become massive. And their new light degrees of freedom, that tower I was talking about, takes over. And the predictions that these Swampland conditions make for present and future is as follows. If we assume the de Sitter Swampland conjecture, we can only be rolling in a rolling potential situation. And moreover, in a short time, we will roll more than m Planck, leading to a phase transition, which you can estimate using fitting the models to the observed cosmological data. You find that the number of e-foldings you're going to get compared to the Hubble scale is 30. So roughly speaking, 30 times the age of the current universe will be upper bound before you hit a phase transition where you get light degrees of freedom. If you assume the Trans-Planckian censorship conjecture, you could have a metastable de Sitter. You could have a metastable de Sitter, but it should decay fast enough. It should decay fast enough, and this lifetime is again given by Hubble scale up to a log factor. And that will give you about 2 trillion years as an upper bound for the lifetime of our universe. So either of the de Sitter conjectures explain one version of the coincidence problem of why the time associated to the measured value of the dark energy, which is 1/root lambda, is so close to the current age of the universe. You see, the lifetime of the universe cannot be much longer. So in any universe where the dark energy is measured, which means that dark energy is a sizable fraction of the universe's energy, you're close to the end of that universe. So therefore, almost by definition, you're gonna have this coincidence problem. You're always gonna be a typical time scale where the dark energy is measurable is related to with the time scale of that universe anyhow. So that's not a mystery anymore. So let me conclude by saying that swampland conditions can lead to potentially observable consequences for particle physics and cosmology. Almost all quantum field theories are in the swampland. Therefore, fine-tuning such as hierarchy problem may end up having different solutions. Severe restrictions on consistent quantum gravity theories of gravity emerge. These ideas suggest restrictions on light matter fields, and moreover, positive energy in the context of quantum gravity lead to local and global instabilities. And this may explain some aspect of coincidence problem. New ideas, and in particular, new dualities may be needed to describe the early universe. Thank you.
Thank you. Thank you for this fascinating tour. And so now the floor is open to questions. And let me see if there are hands raised. Kyle?
Hi, yeah, it was a fantastic talk. The last point that you had, I just wanted to say, in terms of the coincidence, I agree with the kind of logic, I guess, that as dark energy starts to be large, that's pointing to you being close toward the end of that that
Yes.
time frame. But I don't know that I agree with the logic that you can't measure the dark energy. I mean, in practice, that's what our universe is like. But in principle, there's nothing saying that you can't measure, some dark energy that's a small fraction of.
Yes, no, I didn't explain myself very clearly. Let me explain it better. Suppose I told you the age of the universe is the lifetime of the universe is 1/root lambda. And I tell you, get a random time there. Pick a random time where you are there. You're going to get something of that scale. That's all I'm saying. So any scale you're going to measure is going to be of that order. It's very unnatural to get 10 to the minus 10 times 1/root lambda, but it could have been. You're right. But I'm just saying it's not a coincidence anymore. It would be coincidence if it was too small compared to 1/root lambda.
Okay, yeah, that's fine. I mean, I just
that's a better way. I should have said
statement of the measurement. Yeah. Okay.
Yeah, I should have said it this way. Sorry.
That's fine.
Other questions? Matt.
So first of all, thanks for the talk, Cumrun. It's always
Thank you.
very interesting and stimulating. So you mentioned that neutrino masses might, there's this relation to lambda to the 1/4 in the context of some tower of light states. So what about the other states in the tower?
Right. So I wasn't saying that neutrino is that tower. I'm just alluding to these kind of possibilities. So for example, sterile neutrinos and so on could be part of the dark matter and so on. So I'm not necessarily suggesting that this is what it is, but they're phenomenologically then. Some people have actually begun studying those kind of things. It has been studied, for example, in the literature by Keith and all that, DNS. So there are some studies of these possibilities, but I didn't mean necessarily that neutrino mass is exactly that.
Thank you. I see that Kyle's hand is up, but maybe
Yeah, I had a second question if I can. I like this intuitive story about the naked singularities, and you were talking about Maxwell and the kind of screening. And I was just curious what happens to that logic when you're talking about non-abelian theories where things kind of switch around and you have you have confinement and things like that. What does that logic not apply in that situation, or does it still work out?
Well, we usually talk about in the infrared. So we usually talk about whatever left is infrared. So it's going to be harder to describe it in the intermediate scales. So I was talking about the infrared when when you're solving the Einstein's equation and so on. So you usually get confinement or symmetry breaking typically.
Thank you. So while you're thinking for more questions, maybe I can ask one. It's general, but so in your way of motivating these conjectures, it seems that at the beginning you say that these are conjectures that should be valid in quantum gravity, but then string theory and some of the large scale details of string theory entered. How do you, because it seems that the motivation is just by going through examples and seeing that the example satisfies some common criteria. So
yes. So there are more. So as Massimo is pointing out, some of the principles that we have are still not connected to fundamental physics. So for example, like distance conjecture that I mentioned is not, we have not directly related it to facts about black holes, for example, right? So those are the things that I can explain. I can now explain some of it, which, okay, I can, so for example, go there and say there are some loose links, even for those cases, which I didn't explain. So let me try to, for example, describe it for distance conjecture. So we say the distance conjecture says that if you go for a large web for a scalar field, you get some light state. So in other words, your effective theory should break down. Well, what's wrong with having a large field? Suppose there is nothing wrong. Suppose you just have a large scale, large field values, and you go farther and farther away. How do you probe such a thing in gravity? Well, phi has to vary from 0 to a large value. So if you take a most symmetric situation with that, you have a radius r, where phi goes from 0 to some finite value from that 0 to radius r, you find that this costs energy. And therefore, you get a black hole if you go too far away. Indeed, you find that precisely when the range of this phi is of order Planck units, you get inside the black hole. In other words, the variation of the fields which are more than the Planck units are hidden behind the would-be black hole. Now, this is not a proof, of course. I wouldn't claim this is a proof of this statement, but it kind of gives you hints that they are related to black holes. I'll give you another version of the same distance conjecture, which again, this one is again related to black holes. So, so for example, if you take objects in string theory, like brains, they typically have a moduli space. Now, this moduli spaces of these objects, you might imagine could be compact or non-compact, given by some scalar fields. It's easy to argue they have to be compact. Why is the moduli of brains compact? Well, the reason they are compact is that if you view the brains, if you, for example, 0 brains, you can think of them as black holes. So the scalar fields associated with the moduli of 0 brains, for example, should be compact, because if they were not, the spectrum of Hamiltonian on the word line of these 0 plus 1 brane gives you black hole states. And if that space were non-compact, you get a continuous number of states, which is infinite. Therefore, discreteness of the black hole entropy, finiteness of black hole entropy will be inconsistent with a non-compact space for the zero brane moduli. That's an example where you suddenly say, oh, so the objects in your theory, zero brane is also finite. Now, if I could argue that 3 brane is also finite, that will give you almost a distance conjecture, because 3 plus 1 brane is our universe. So that's almost in that same thing. Again with black hole. So this is what typically happens. There's some loose connections, but we don't have a full picture of that to make it really tight.
Thank you. I see Xu Cheng.
Yeah, I have a question about you have said when we go to the large field, then it's, even though we construct a DS vacuum, then it will tunnel to the it's metastable into a tunnel. I'm just wondering, will the Swampland conjecture give the constraint of how large the potential barrier is? Because it seems if the barrier is large enough, then we can just make our universe.
Yes. Yes, so let me just bring back the point that we were describing. It was here. So let me first of all go back to your picture that you're asking. It's somewhere, is it here? Yeah. So this is a distance conjecture, and then we came here, talk about the potentials, and then over there we talked about the fact that you could have a metastable de Sitter space. So what you're asking is whether or not we know about this height and what is the lifetime. So it depends on which conjecture we take into account. I mean, there are these 3 possibilities that I was saying. If it's condition 1, I can't say anything about it. If we believe one of these 2 conditions, well, then one of them is that basically you cannot have a metastable one. But if you do have, this one is allowing it. But it turns out that Trans-Planckian censorship conjecture puts an upper bound for the lifetime, which is this value. What that means is that the height of that barrier is not large, because the lifetime is just the, so usually when you have a computed barrier, it's e to the minus the action. This basically tells you that the action is order 0, so it's very small. So therefore, what that means in particular is that if there is in fact a metastable list, that there is almost possible to get rid of it. So it's a bump really, at best, supporting it, not bigger.
Thank you very much.
Thank
you. We have other questions.
Someone has asked me to upload my presentation. So if I can give you Massimo, would that be possible, or what should I do?
It will happen. I mean, it will be done automatically, I think. Because I know that our personnel does it. So after 1 day, it will appear in the list of the seminars. So,
I think he means by like the slides itself, not
the file itself. You can send it to me, even though I don't know how to upload it, but at least I can send it to people that can upload it.
Okay, I will send it to you, and then anybody who wants it can ask Massimo. That's okay.
Okay, so any other questions? So actually, maybe I didn't follow, but what is the role of black holes in the completeness conjecture? The one that says that all charges should appear in a.
I seem to have been muted. So if you take a black hole, we don't trust the black hole solution if it's small. But if you take a big black hole, we trust it. Charge order 1, 2, it's quantum. So we take a big mass, big charge. The classical description of black hole is valid. So take a big black hole, big mass, big charge. So let's say charge, you choose a charge to be Q. And take another big black hole with charge mass some charge m prime, mass m prime, and charge q minus 1. So antiparticle minus q plus 1. I mean, negative q minus 1. So these two black holes, both macroscopic, one of them has charge q, the other one has q minus 1, q minus 1 with the opposite sign. If you collide them, you get charge 1 state.
So this is based on the assumption that black holes exist for any charge.
That's because the classical GR tells you.
Because, but as we know, the classical GR says that black holes exist with continuous charge. And then
No. So, but by classical, I mean semi-classical. Like Bekenstein-Hawking entropy and all that are semi-classical consistency of black holes. So take a classical black hole and study semi-classically. So that will give you already consistency of semi-classical black hole already quantizes Q.
Okay, so this is based that everything that can happen will happen.
Yes.
Thank you. Other questions? And maybe another one. The cobordism conjecture, or the conjecture that there is only one gravity, is again based on the experience from string theory and from M theory, imagine. Or can it also be reduced to ultimately to black holes?
Well, it's related to the fact that there is no global symmetry. So global symmetry is what we call the zero form symmetry. Well, you can have associated particles, but you can extend it to like one brane symmetry with associated to strings and or one-dimensional objects, and to two-form symmetry, and so on. So there are various arguments why higher form symmetry should also be absent, global symmetries. If you take that view, then if you apply it to three-form symmetries, then that means that there is no charge distinguishing any 3 + 1 dimensional space from any other. If there are two inequivalent cobordism gravities, then you can associate a charge to the 3 + 1D space, and that will be inconsistent.
Thank you. Any other questions? We had actually a nice discussion, but we can have any. If not, I don't see any. Let's thank Professor Vafa again. It was great to have you here. I hope that the next time will be in person.
Thank you. I enjoyed very much, and thanks for coming to my talk. I hope to see you all in person as well, hopefully soon.
Thank you.
Thank you.
Thank you.
Thank you.